Okay, so in reviewing for the test it'll open up on Monday. You'll need to know, make sure you understand questions 1 through 5, questions 8 through 10, and then 18 through 23. 25 through 27, 29, 30, and 33. You will have questions very similar to those in the multiple choice section of the test. You will be allowed to, as I put in the update, you'll be allowed to use your notes, your AP reference sheet, and your textbook. So you want to have those things printed off sometime between now and Monday. I'll open up the test on Monday, probably Monday afternoon. And then you'll have from Monday afternoon to Wednesday night at 11:59 to complete the test. Using those resources, your textbook, chapter 15, your student notes from the student notes folder in Unit 7, and then your reference sheet that comes off the first page when you open up the home page. There's a link for the AP reference sheet. So you want to have all that information there. It's going to be timed and it's going to be on the lockdown browser, but it should be plenty of time for you to answer it. It'll be somewhere around 120 minutes, which is longer than a regular class period. So, but with you having the opportunity to look things up in your book, I wanted to make sure you had enough time to do all the multiple choice and the free response. There are 15 multiple choice questions and one long free response question. Okay. Um, so that's just some information about the test if you haven't heard that yet. So, does anybody have any particular questions on the practice problems that you want to go over? We'll look at those first, and then if there's any other questions, we'll address those after the practice problems. Anybody have any questions on the practice problems? We went over some yesterday, but I know we didn't do all of them. Nobody has anything? Make sure you do that you are aware of this little, we talked a little bit about this yesterday, of this little symbol here, because you will see that on some questions on the test. The delta H being greater than 0 or the delta H being less than 0. That is important in determining whether something is an endothermic reaction or an exothermic reaction, which is going to be important in determining what happens if you raise the temperature or lower the temperature of that reaction. So make sure you have that jotted down. Yesterday we looked that up. A delta H that's greater than 0 means that is an endothermic reaction. If it's endothermic, that means heat is a reactant, and it would go on the reactant side of the equation. So we could write plus heat over here because that's an endothermic reaction. So that would mean if I were to increase the temperature here, that would be like adding heat, and that's going to drive my equation to the right. Okay. If this reaction or this equation were to have said delta H was less than 0, then that would have been having heat as a product. So if we increase the heat, that would have drove the reaction to the opposite side. Okay. So just make sure you're squared away with that. That can get a little confusing. And that's just memorization about which one is which. So you want to make sure that you have that correct. Let's see. Of course, knowing your formulas for setting up K and for setting up Q, the reaction quotient, and knowing how those things are affected. How is the reaction quotient related to the K? And I like the little mnemonic device they gave, where if K is greater than Q, then that means the reaction is going to go to the right, that the less than sign is pointing in that direction. If K is less than Q, then the reaction is going to go back to the left. That's just a little mnemonic device to help you remember which one it's going to go, which way it's going to go, because most of the time with the question, that's what they're going to ask you. Here's K, find Q, and then based on those two values, determine or predict which way the reaction is going to go. So, let's see, KSP. A lot of people had questions about KSP yesterday. The KSP, remember, that's the solubility product. So it's just taking a compound and seeing how soluble it is in water. And so KSP is always just going to be equal to the concentration of your positive ions, whatever that is, times your negative ions, whatever that is. Okay. And the thing with the coefficients would apply as well. So if if in the equation you had a coefficient of 2, then you would raise it to the second power. The other thing to remember, so like if we took this as an example, and cobalt chloride split up into cobalt ions and 4 chlorine ions. Okay, so if you did that and you put these in here, you would have the concentration of the cobalt ions, but then you would also have 4 times the concentration of the chloride ions, and then it would also be raised to the 4th power. Okay, because when that splits up, you have 4 times as many chlorines as you do cobalts. Okay, so that's all there is to KSP. It's the same basic formula as all the other ones, where you're going to put products over reactants. But in the case of KSP, our reactant is a solid, so it's not going to be, there's not a concentration for it. It's only the things that have the aqueous, the AQ beside them, the things that will split up, that will have a concentration associated with them. And so they're the only things that are going to wind up in that equation. Okay. Let's see, what else just in general. There's our endothermic, exothermic thing again. So again, make sure you understand which one is which. Le Chatelier's, there'll be several Le Chatelier's principles. So go back through that. The general overview of Le Chatelier's is if you increase the stress, and stress can be concentration, it can be pressure, it can be temperature. But if you increase the stress, the reaction is going to go in the direction to relieve that stress. So if you're adding more product, the reaction is going to go back to the left to use up that product. If you're adding more reactant, the reaction is going to go to the right to use up that reactant, and so that you get rid of that stress. Let's see. With these type equations, like you see on 23, just remember that you're basically just combining those two equations to get this one, and you may have to manipulate those somehow to get the end result. So you may have to turn one around backwards. So like the second one here, K2, if we turned K2 around backwards, we would have the CuO, the copper oxide, on the left, which is what we want to get to. And our Cu2Os would cancel out because they'd be on opposite sides. Yeah. So you may have to wind up manipulating these things. And if you turn an equation around and you reverse the equation, then you're basically going to take the inverse of the equilibrium constant. Okay, so let's see. Let's work that one out because yes, that's what they did. So they turned this equation around and got 1 over K2. And then they basically took the square root of the first equation to get the correct K1. And then you just multiplied those two together. So let's see. 4Cu plus O2 goes to 2Cu2O. And then if we turn this one around, that would be Cu2O plus O2 goes to CuO. All right, so 2Cu plus O2 goes to 2CuO. Okay. So if we took half of this one away, which would be the same as like taking the raising it to the 1/2 power. So we took half of it away. So divide that in half and that in half, and that would become a half. Then when you add these two things together, you would have those canceled out. You would have 2Cu plus an O2 plus 2CuO. This would be K raised to the 1/2, and that would be the inverse of K because we turned it around backwards. Yeah. Okay. So just know on those that you're going to have to wind up manipulating them. You may have to wind up turning in an equation around backwards or doubling it or taking half of it or reducing it by half or something like that to get the ending equation that you want. And then you'll just wind up combining those K's. Okay. And then we kind of talked about most everything else. So I'm going to open it back up for y'all. Do y'all have any questions on the practice problems that you want to go over?
Can you explain number 11, I think?
11? Okay.
Yeah, I don't know if you have to do a rise table to find out the numbers, or if it's just, I guess, if it's just like, I guess, theory. Like, you have to find the actual numbers to know.
Okay. Let's see. All right, number 11. A 2 mole sample of carbon monoxide and a 2 mole sample of water are introduced in a previously evacuated 100-liter rigid container. The temperature is held constant as the reaction represented above reaches equilibrium. Which of the following is true? Okay. All right. So if it's a 100-milliliter container, we can find the molarity by dividing each of those numbers by 0.1. Are you asking me, does it want you to do a rice table, or is that what you're asking?
Yeah, I guess how would you find the answer? Because it says, like, it doesn't show any numbers in the answer, but it does have, I guess, like, numbers, I guess, like, which is bigger than the other.
Right. So, yeah, it's I don't know that we need to work out an actual rice table, just because in my answers it's just asking for greater than and less than. Um, which of the following is true at equilibrium? Okay, so we have equal amounts to start with. Our equilibrium constant is definitely greater than 1. So I would say that this is going to proceed to the right. So if it's proceeding to the right, then you will be making CO2 and H2. I would cross out, if we're using process of elimination, I would definitely cross out D, because at equilibrium does not necessarily mean they are all going to have an equal concentration. That won't happen. Concentration of water is greater than the concentration of CO. Concentration of CO2 is greater than the concentration of H2. This is a 1-to-1-to-1 ratio too, so temperature is held constant. Okay, so they are going to, in that case, they're going to use the Q and the K relationship there. So you would use those initial numbers and put those into the reaction quotient, which is the Q, and see how the reaction quotient compares to the equilibrium. And then that will tell you if you are going to the right or to the left. And then from that, you can look at the choices and again use process of elimination to figure out which one is the best option.
So it's not because the K is lower than 1?
Well, the K is not lower than 1. The K is 1.5 times 10 to the third. The Q, though, let's see, what does Q turn out to be?
Sorry, I put a negative above that.
Oh, yeah, no, it's a positive. So 2 divided by 0.1 would be 0.2, right? No. 2.0 moles divided by 0.1 liters. Nope, it's not 0.1 because that's not milliliters. Sorry. Okay, so Q is going to be your concentration of CO2 and H2, which we don't know. Yeah.
I have a sorry.
I think, yeah, if we look at that, you can see that this is going to proceed to the right. So at the end, your concentration of CO2 should be greater than your concentration of carbon monoxide, since you are making the CO2. I think that's what they're trying to get at.
So if the K is more than 1, then it's going to the right or the left?
Yes. If the K is greater than 1, then that reaction is going to happen and in the forward direction. It's going to move to the right.
Does it also mean that there's more product? I guess
There's more
If
product.
the K is larger than 1.
Yes, there would be more product forming than you would be using up your reactant and forming your product. So yeah, the key term is introduced to recognize the system is not at equilibrium. Since there is carbon monoxide, the reaction will sift to form the product. Yeah. Q is less than K. The system is not at equilibrium. So reactants are going to form products. And then until you reach an equilibrium. Equilibrium is when your reaction quotient and your equilibrium constant are the same or are equal. And that's not the case at present. And it's
I mean, well, it says
difficult to tell
the
that.
problem that CO and H2O are added to the reactant side, so wouldn't that form more products because they were like expressed on that side?
The 2 mole sample and 2 mole sample are introduced. Container temperatures held constant as a reaction. So we're talking about number 11, right? Make sure we're on the right one. So in number 11, it really doesn't tell us. It doesn't tell us anything else other than our starting conditions of our reactants and that our temperature is held constant. As the reaction above reaches equilibrium. So from the way it's worded, it's not currently at equilibrium. So if it's not at equilibrium, then our reactants are going to make products. So our concentration of product should be greater than the concentration of the reactant once it reaches equilibrium. Because it's definitely, with that being such a high number, it's definitely going to go to the right. And I think that's what they wanted you to recognize, is that you're not currently at equilibrium. And so since you're not at equilibrium, you are going to form products. And that's what they wanted you to see. But that's not the greatest question in the world, for sure. Key term is introduced to recognize that the system is not at equilibrium. That's the best explanation I can give you right now, and knowing that if you have a question like that on the test, you will have more information than that. And the point of that question was just so that you recognize if something's not at equilibrium, it's going to move in the forward direction until it gets to that equilibrium. So.
Okay, thank you.
Yeah, that's not a good question to me, but I didn't write it. Okay, we got another one.
Can you go number one?
Number one. I will try. Number one. Okay, barium sulfate is least soluble in a 0.1 molar solution of which of the following? Okay, so with that, we're talking about barium sulfate, which is not, is normally not a soluble thing anyway. So if you put barium sulfate in water, most barium compounds don't dissolve in water. Okay. So normally it's not going to do that. Not a lot that we can see anyway, but even just a tiny little bit might split up into barium and sulfate. Okay, so if we put some of it in water, you might have a tiny little bit that'll split up into barium ions and sulfate ions. Okay, let me change that because that looks like an 8 instead of an S. There we go. So it's saying if we had something else in the solution, which one of those 4 ions, if we added it to the solution, would make the barium even less soluble than it already is? Okay. Would it be adding more sulfate, adding aluminum sulfate, ammonium sulfate, sodium sulfate, or barium chloride? Okay, so all of which are soluble in water. So if all of these are soluble in water and they all split up, what do they split up into? Sulfate and aluminum, sulfate and ammonium, sulfate and sodium, and then chloride and barium. Okay. So which one of those things, if you added it to this solution, would make your reaction go back to the left? Because that would be least soluble, right? Making it so that the two things come back together and form barium sulfate. So that's basically what the question is asking you. Which one of these, if you added it to this solution, would make your reaction go back to the left the most? So which one do you think it would be?
I don't know.
All right, so look at the formulas. If you want this to go back to the left, what do you need to add on this side, on the right side? What do you have on the right side? What 2 things do you have on the right side of this equation? Barium and sulfate, right? So if you added either one of those 2 things, that would be an example of Le Chatelier's principle. We're adding more product, which is going to make the reaction go back to the left, right?
Mm-hmm.
Okay, so which one of our 4 choices is going to add the most barium or sulfate? A. Okay. So why did you choose A?
Because the sulfate is multiplied by 3, I guess.
Because we have 3 of them, right? In B we only have 1. In C we only have 1. And in D we have 1 barium.
Mm-hmm.
So let's see if the correct answer is A. That would have been my choice as well. So, yep. Yes, it is A. Okay. Because if you add anything to this right side, it's going to cause the reaction to go back to the left, which means making more barium sulfate, which would make it less soluble. Because if you're making more of it, then it's going to pile up there in the bottom of the beaker. And the aluminum sulfate has 3, where the rest of them, they don't have as much. Does that make sense?
So you want more solid?
In this case, I want more solid because that would make it the least soluble.
Okay.
More solid means less soluble. So in this situation, that's what I was looking for.
Okay.
Okay. Yeah, these solubility ones are weird because you're adding it seems like you're adding random stuff, but you've got to break it down to its ions. And then you realize, oh, well, if I'm adding more sulfate, that's like adding a product. And so I'm going to drive it one way or the other. Okay. All right. Good question. Next. We have another one. We don't have to do these practice problems. If you have a question about something else, we can cover that too.
Can you do number two?
Number 2?
Yes, ma'am.
Okay. Yeah, this is a good one because you'll have one similar to this. Now, not similar compounds or anything like that, but a similar situation where you're given a reaction. You'll be told that, hey, I've got these 2 colors here, and I want to know what's going to happen to the solution when I make a change. Is it going to be this color or that color or what? So which of the following occurs when excess concentrated ammonia, this one, is mixed thoroughly with 0.1 molar copper nitrate? Okay. So copper nitrate, what you need to understand about that is copper nitrate is basically your Cu plus ions. That's how they get the copper plus ions, is it's in the form of copper nitrate, which is soluble. So in the solution, you put your copper nitrate in there and you have some copper ions and you have some nitrate ions that are floating around in there, okay? So that's where the copper 2 plus comes from. So now what they're asking is what's going to happen if I add more of this, okay? So the copper solution is light blue. This copper tetra ammonia weird ion here is going to make the solution deep blue. So I'm adding more of this. Which one of these is going to happen? A dark red precipitate forms and settles out. A solid layer of immiscible liquids form with a blue layer on top. The color of the solution turns from light blue to dark blue. Bubbles of ammonia gas form. Okay, so think Le Chatelier's. If we add more reactant, what happens to the reaction? Which way is it going to go? Right or left?
Left.
You're saying if we add more of this, the reaction is going to go back this way?
No, the other way around.
Right, yeah, okay. Yeah, it helps sometimes to draw it out. So if we add more of this, we're going to go in this direction. So if we're going to the right, what's our solution going to look like visually? What color is it going to turn?
Darker.
Dark blue. Yeah, it's going to turn dark blue. So we can take out A and B because they are not applicable to this situation. We don't have anything about precipitates or dark red colors or anything like that. Bubbles of ammonia gas, they're not forming, they're already there. So we're not making ammonia. Ammonia is the reactant. So C, going from a light blue to a dark blue, is our correct answer. Okay? So look at the equation. Look at what they're saying the change is, and then think about Le Chatelier's principle. If I add a reactant, moves the reaction to the right. If I add a product, moves the reaction to the left. Okay? That makes sense?
Yes, ma'am.
Okay. All right. Anybody else?
Can you re-explain why that's a reactant for that equation?
For this one?
Yeah.
Because it's on the left. Reactants are always written on the left. Products are always written on the right.
No, yes, ma'am. I know that, but like in the question, the CU and O32, how do you know that that's...
Oh, how do you know that is? Okay. Because that's in our reaction, we have a source of copper ions. And in my question, that's the only thing that has copper there. I just basically kind of use process of elimination. My product is not a nitrate. My product has the NH3 with it, not the NO3. So the NO3, the copper nitrate, can't be part of my product because my product does not have the NO3 in it. My product has the NH3 in it. And I have to have some copper ions, and this is the only thing that's given in my problem that has copper ions. That's the only reason I chose that. Okay. Yeah, good question, because that does look weird. You look at the equation and it's not quite the same as what the products are. But again, think about our solubility of, we take this ionic compound here and if we put it in water, and that's what that little AQ means, that automatically means that splits up. All nitrates always split up into copper ions and nitrate ions. So that is my source of copper ions. I can't just have, I can't just have ions. Ions are always in combination with something else until you dissolve them in water or do something to them to separate them. So this is what's sitting on the shelf in the chemical stock room. And when I put it in water, this is what it actually becomes, copper ions. Okay. So I know that can be a little hard to see sometimes, but just look for your little cues, like the AQ is the big hint for that you dissolved that in water. Okay, next question. I will give you this little hint about the free response question. You need to go back and make sure you know how to change grams to moles, and then make sure you know how to use the ideal gas law. Okay. The rest of it will kind of cover things that are in the equilibrium chapter. But you are going to have a situation where they're going to give you, 5 grams of hydrogen. I'm just making stuff up. And then they're going to give you information about pressure and volume and temperature, and then you're going to need to know the moles, okay? Because in all of these problems that we do, we have molarity. Remember, capital M is molarity, and that is moles per liter. So in all these problems, I have to find moles. Well, they did the, very mean thing of giving it to you in grams. And so now you've got to convert to moles. So go back and remember that. That's going to be your railroad tracks. And we go from grams to moles by just using the atomic mass, the molecular mass. So for hydrogen, each hydrogen atom is 1.008. I have 2 of them, so that would be 2.016 grams of hydrogen in 1 mole. And then that gives me my number of moles. And then I can plug that into the ideal gas law and find what I'm looking for. You were looking for one of the others. But if you didn't know to change grams to moles, you would think, oh no, I've got this equation and I have 2 unknowns and I can't solve for 2 unknowns. But you really don't, because you can change grams to moles, put that in ideal gas law, and then solve for what you're looking for, and then use that in the rest of the problem. Okay, so if you need to, brush up on that, make sure you know how to do that.
Miss Tater. I know that there's like the 22.4 or whatever, and I always try to plug that in somewhere and do it wrong.
Yes.
Where does this come in?
Okay, the 22.4.
What is that?
22.4 is the number of liters of gas that's equal to 1 mole of a gas at standard temperature and pressure. So that is that is a good thing, a useful thing if you're at standard temperature and pressure, which standard temperature is 0 degrees Celsius or 273 K. Standard pressure is 760 millimeters or torr, or 1 atmosphere. Now, if you're not at those conditions, that conversion is not true. Okay? So this fact of 1 mole of a gas being equal to 22.4 liters is only true at those conditions. So it's useful and it's a good thing to remember. And I think it's on your reference sheet. I'm not sure. But it's only going to come into play when you have standard temperature and pressure.
Okay, thank you. I was trying to use it, and I'm like, wait, where am I using this? But that makes sense.
Yeah. Okay. It's basically, you take this equation and put in 273 and put in 1 atmosphere and put in 1 mole. The volume you will get will always be 22.4 liters. But again, if you're not at those conditions, then your moles are not going to be, it's not going to work out. You can't say that. Okay.
Okay, I have a question. I know this is a dumb question, but how do I know which side has more like moles? You know, like when they're like when the pressure, like
right.
you pick the side with the fewest or most moles, and then like I don't know how to do the ones where it's like both sides. Like one side has like something with like no coefficient, the other side has like something with like a 2 coefficient, and like it's one thing, so I don't know which one has. I don't know.
Okay, all right. So in an equation, if there is no coefficient that's actually written there, it is understood to be 1. So this equation, for example, there's no actual numbers written in front, so those are understood ones. So there would be 2 moles total on this side, and there would be 2 moles total on that side, which that for your example, that just there are equal numbers of moles on both sides. So that's not a good example for that. But as far as how to count those out, that's what you do. You just look at the coefficients in front, and if there's not a coefficient, it's an understood 1. Did that answer your question? Or
yeah, I was confused.
Yeah, it's if there's nothing there, it's understood to be a 1.
So I just count the coefficients.
Yes. Yes.
Okay.
Mm-hmm. That's what you do. Yep. Let's see if there's a. No, that one's not good either. They're all coming out to be the same number of moles on both sides. Okay, this one. If you look at number 7 and use that as an example, I would have 2 and 1. I would have 3 moles on this side, and I would have 3 plus 1. I would have 4 moles on that side. Total. So that would be one of those cases where if you would be going to either the side with the greater number of moles or the side with a fewer number of moles. That's how that would work out. Does that make sense how I did that?
Yes. So, like, if temperature increases, that means it's exothermic or endothermic.
Okay. No, you're thinking backwards about that. If the temperature increases, you have to know ahead of time if it's an endothermic or an exothermic reaction. Okay? The temperature increase is not going to tell you if it's exothermic or endothermic. You have to know that already. Okay? So what they're going to give you in the problem is they're going to give you an equation. They're going to give you some conditions like delta H is greater than, They might be nice enough to tell you it's exothermic, which would be really nice, but they're not always nice. They're going to give you conditions like delta H is greater than 0. What you're going to have to do is remember that, okay, delta H is greater than 0. That is an endothermic reaction. And if something is endothermic, that means heat is a reactant. So I would, in my equation or on paper, I would literally write down plus heat on the left side. Okay. And then they're going to say, all right, so that's your equation. Now we've changed the temperature. We've increased the temperature. What happens to the equilibrium? So then you would be thinking, okay, I figured out this is an endothermic reaction. If I increase the temperature, I would be increasing the reactant of heat. would be increasing the heat. That is a reactant. And anytime I increase a reactant, my reaction is going to go to the right. And then I would use that to answer my question. Okay. Or the opposite case. So they're not going, so raising or lowering the temperature does not tell you that it's endothermic or exothermic. Okay.
So wait, so then how does temperature, like, okay, if it doesn't, like, let's just say, hypothetically, the problem was, like, the temperature rose, like, does that affect the equilibrium at all?
Okay, it's going to be how it's worded. Okay, I know y'all hate hearing that, but it's how it's worded. So if the problem said, here's our reaction, and this is our equilibrium constant or whatever, and then we ran another trial and we increased the temperature, then you got to think, okay, this is the Le Chatelier's. I need to figure out which side, if it's endothermic and or exothermic, and then that'll tell me which way the equation's going. If they said something like, all right, we had these two reactants, X and Y. We put them together and the temperature increased. We didn't increase it. Okay, you see my difference in my wording? We didn't increase the temperature. The two things just came together and the temperature increased. That means that that thing is giving off heat. And if it's giving off heat, it's an exothermic reaction. And then the rest of the problem would go on to say, and then we did another trial where we increased the temperature, before the reaction started, we increased the temperature, what happened? So you got to be really careful about how they're wording it, as far as, is the temperature something that we as the people in the lab changed and then you get to a new equilibrium? Or is it something where the two things just put together and the temperature increased naturally because it is an exothermic reaction or an endothermic reaction? So most of the ones on your tests and the ones in these practice problems are going to be worded like this, where they're going to say, here's a reaction, here's the delta H of the reaction, and then you need to know, okay, that delta H greater than 0 means this is endothermic, which means I'm having to put in energy, which means heat is a reactant. So then if I change the temperature in my next trial, how is that going to affect the reaction? Did that help explain the difference between the two?
Yeah. I was just kind of confused about that.
Yes, it can be. Yeah, I can see that. But you gotta think about how it's worded. Did you increase it, or did it just increase all by itself?
Okay.
If we increase it, then we're doing Le Chatelier's. We are changing that equilibrium. So. Anything else? Is there a good question?
For explanations, are we going to have to say that it was Leigh Chatelier's? I don't know how to say his name, but are we going to have to put his name in there?
They would like for you to use his. You could use his principle, and you could just use that name instead of having to say the principle. Write it out. So either you're going to have to say, according to Le Chatelier's principle, the reaction is going to go to the right, or you're going to have to fully explain that and say, we know if we add a reactant, then that means the reaction is going to move to the right. And if we add, so either way would probably be okay. You could reference it using just his name and finish out the explanation, or you can give me the entire, explain the whole thing if you don't want to use his name. And I don't count. I mean, they're not going to count off for spelling. So if you spell his name wrong, it's fine. I spell it wrong all the time. But
okay.
yeah. Just get close to it because there's there's no other name like it. So if you just get close to Le Chantelier's, you'll be fine. Anything else?
Okay, just one more thing. How do I know when to use a rice table and when not to use a rice table?
Ah, yes. Good old rice tables. There's a love-hate relationship there. All right. We talked about this a little bit yesterday. When you have a KSP, because let's scroll down to some of these KSP problems. I believe in one of the ed puzzles on solubility, they were using a rice table with a solubility problem. And to me, that's not necessarily, it's not that, those aren't as complicated. And so I don't know that I would use a rice table with a solubility problem. I would definitely use one when you are making some change. They're giving you an initial set of conditions, they're changing something, and then they're giving you equilibrium conditions, or they're asking you to find equilibrium conditions like concentrations and stuff. Then I would use a rice table. Other than that, I don't know that I would. Let's see. I'm going to pull up the notes and see if we can get to the notes, and that may help us distinguish between the two. And technically, you don't have to use a rice table to solve the problem. It just makes it a little easier. That's supposed to be the intent, is just to have an easier way to solve the problem. But you don't have to do it that way. So, are you able to see the notes? Did my screen change for y'all? Yes? No? Maybe?
Yes.
It did. Good. Thank you. Okay, come on. Come on. I believe it's page 6 that they started introducing those on. Yeah, 7. So basically, the rice table is if you have an equation, you have a change, and then you're asked to find something with equilibrium. So you see in this first example, they give you the initial conditions. Then they tell you something about the equilibrium conditions. And then they ask you for this one asks you for the equilibrium constant. Sometimes they'll ask you for the product's concentration or something like that. So those are where it becomes easier to use a rice table because you have it laid out all kind of in front of you and it's not all jumbled up in your head. So in that situation, I would use a rice table. But yeah. And here's another example the same way. You're asked to find, you're given the equilibrium constant this time. You're given your initial conditions. There is some change. The reaction takes place. There's some change. And then here's your equilibrium. And you've got to find what X is. You've got to find out what that change is. So those situations, it's easier to use a rice table than try and figure out any other way. But when you get to KSP, the solubility product, if you don't want to use a rice table, I don't know that I would because those are very simple type equations. So like here's a KSP. So the equilibrium constant is just the concentration of the two ions. And so they're much easier. If you make some change, then our change is X, and you don't have to go through all that process. So for solubility ones, I wouldn't necessarily use a rice table, but for the other ones, I would. Do you want to go over some of those rice tables, or you know how to use them, you just don't know when to use them, or do we need to go over how to use them?
Yeah, I just didn't know when to use them. I think I understand how to use them.
Yeah. Okay. Yeah. I would use them for anything other than maybe a KSP, a solubility product. I probably wouldn't use it there, but anything else I would. Okay. Is there anything other than these practice problems that you want to go over?
Can you go over the FR on the AP daily videos, one of the FRQs where it's like draw the graph or something?
Mm-hmm. Yeah. Let me pull that up. Get signed into it.
I just was curious of what like the graph actually looked like.
Mm-hmm. Is it the? I think I know which one you're talking about. Do you remember what number that was? The one with PCL. It wouldn't be the one with PCL 5. That was just drawing it out. Trying to think which one that is. Um, 3 or 4, or let's try 3 and 4. Is it this one?
Yes.
That one. Okay. All right. So with that one, experiment was repeated by this time with 4 moles. Okay. All right. So with this one, what they want you to do is draw how it's going to change over time. Well, if you go back to you've doubled this, you've doubled the solid, but you need to remember that your equilibrium constant is dependent upon the pressure of the gas, not the amount of solid that's there. So it's still going to be a line that starts at 0 and goes up and levels off at 1. Because if you go back to the original problem up here, it tells us that our vessel is at a constant 1 atmospheres pressure. So we're not changing the pressure of this gas. It doesn't change pressure. That means you're only going to make that certain amount of CO2, and that's it, regardless of the amount of this that you start with. Because our equilibrium, as far as equilibrium goes anyway, because our equilibrium constant is only dependent on the pressure of the CO2. That's it. Okay, so that's why our graph is going to be essentially the same. It's going to start at 0 and it's going to rise to 1 atmosphere and then it's going to level off because that's your constant pressure. Okay, does that make sense?
Mm-hmm.
Yeah. They try and trip you up there with increasing this number, but they want to see that you understand that if it's at a constant pressure, it's going to go up to 1 atmospheres and that's it. It's not going to go up anymore. And so they want you to know you're going to rise and you're going to level off, and that your equilibrium constant is only dependent upon the pressure of the CO2, not the amount of solid that you started with. So,
is this the same question where it was like if pressure, no, if temperature remains, like if it's like something in a box and temperature remains constant, will the pressure increase, decrease, or neither?
I don't think this is the same one.
Okay.
When heated thoroughly, how would I say it's represented? Placed in a rigid 100 volume, 100 milliliter, 100 liter reaction vessel. The vessel is heated, which time the pressure is held constant at 1 atmosphere. Okay.
No, I don't think
So
it
no,
was
you're not.
the
Yeah,
same.
you're not changing anything on this one. All right. So let's. Do you want to go over that one?
Yeah, that was like one of the ones I got wrong on that FYQ, so I was curious because it was like if the pressure, if like the box is constant and it's closed and the temperature's the same over the reaction, will the pressure decrease, increase, or remain the same or something? I don't know.
All right, let's see if we can find it. Now that's a multiple choice. No, wait a minute. There's more questions. That's multiple choice. Multiple choice. It's not any of those. Is it the one on the PCL5? I don't think so. 6 molar samples placed in previously evacuated. No. Okay, all those are multiple choice too. Okay. Well, it must be one of these two. Was it a free response question?
Yes, ma'am.
Okay.
I think it was 7.7, 7.8 under the PCL
Oh,
stuff.
it was that one? Okay, I was right there.
Yeah,
Go ahead. I haven't assigned them necessarily as homework, but I do have progress checks for Unit 7 opened. If you want to use those as like a practice test or something, you can. So that one. So this one you just draw it. Okay. So and that's going to be the shape. The graph, this is the one where they're going to slope down and slope up. Reactants will slope down, products will slope up. Okay, here we go. As the reaction occurs at constant temperature, does the pressure inside the container increase, decrease, or remain the same? And explain. Okay. So I've looked at this 500 times, but I can't remember all the answers. um, All right, so this is what you were talking about earlier when we were talking about the coefficients of the reaction. So if the temperature is not changing and this reaction is coming to equilibrium, the reaction is always going to proceed to the side with the lowest pressure, and that would be the fewest number of particles. Okay. So this are the fewest moles of particle. So this reaction is going to proceed to the right side because over here I have 2 moles of things and over here I just have 1 mole of things. So if this reaction is proceeding to the right, which it is, because here's my K, it's greater than 1, so more than likely this is going towards the right. And if that were to happen, I'm going to go to having a fewer number of moles. If I have a fewer number of moles, then my pressure is going to go down. And my pressure is going down because I don't have as much stuff packed into that same volume of space. Okay? Yeah. But let's check and make sure my thinking is correct while looking at the answer. Okay. All right, so yes, the pressure is going to decrease. It's going to go down. And the justification for that, or the reason for that, is there are more moles of reactant than product. So it's going to move to the side with the smallest number of particles or smallest moles of particles. And when you do that, that's going to decrease the pressure. Okay, does that make sense as to why it would decrease? So if you go to, all right, so if you look at this box, this is our rigid container, and these are our products in it. This is our at equilibrium. So if I can make this reaction use up some of these reactants and form more of these, I'll have less number of particles to run into each other, and that's going to reduce the pressure.
So okay, so I thought that it was the same because they had just like the same number of particles were still in the box, I guess. Because like you don't change, like you don't use up. I mean, like you technically, I don't know how to explain it, but like
I know I know what you're thinking is law of conservation of mass. You have the same number of atoms here, right?
Yeah.
The thing is that those atoms are not all separated anymore. So when we started, okay, so when you start this, you have a bunch of these PCl3s and you have these Cl2s. But as the reaction proceeds to the right, you make a lot of these PCl5s, which is combined. It's like taking 2 particles and combine them into one big one. So you have fewer numbers of particles. Yeah, you got the same number of atoms. And if they were all individually floating around, then nothing would change. But they're not. They're crammed together, shoved together, and made a new compound. And you have fewer of those compounds. So you have fewer number of particles floating around in that same volume of space.
Okay, yeah, that's
Okay.
what I was confused about.
Yeah. And to make it easier, just go back to the equation and look at the equation. There's 1 mole here, 1 mole. That's 2 moles that you start with. But when you end up in the equation, you only have 1 mole. Same number of atoms and stuff. Law of conservation is still good, but you have fewer number of those things. So that reduces the pressure. That's a good question, though. So a lot of people miss that one. A lot of people put that it would stay the same. Anything else? Ooh, I need to check my roll. We have now got 12 people in here. I need to make sure that I add you to the roll. Carson is here. I need to add him. Noah is here. Is that it? So Tyler, Reese, Owen, Noah. I think I got everybody else. Yeah. Okay. All right. Anybody else got a question? See, on the free response question, you will need to know how to do an ICE table. I'm looking at how I worked it out. And you will need to know to use an ICE table or a RICE table, however you want to say it. You'll have to use the ideal gas law. So you want to, and that's given to you on the formula, but on the formula sheet, but let's see. I think that's really the only problem that you will have to use a RICE table on is that free response question. The other ones, you can use it if you want to, but you don't necessarily have to. Any other questions? Let's see, I'm trying to think if there's anything I haven't told you that you need to make sure that you know how to do. I think we've covered everything. You know, as far as like the little obscure things that you're like, how in the world would I know? I think we've covered those things. Like I said, I told you about the delta H, less than 0 and greater than 0. Make sure you remember that. Or at least know where to find it in your textbook. That's the other thing that I did want to tell you is look through. You don't need to read the entire chapter. I don't want you to do that necessarily. But in chapter 15, you do kind of want to know where things are. You know, it's an open note test, but you don't want, but you're on a time limit. So you don't want to waste all your time reading the entire chapter looking for something. You want to kind of know where things are and know where to go as far as just broad general terms, where to go to answer that question. So I would maybe go back through my practice problems or maybe go back through my topic questions and have my book out with me and just kind of look through and it's like, oh, okay, this is a KSP problem. So kind of where do I find KSP in my book? Just familiarize yourself with your textbook so that you're not wasting a lot of time searching through things and going through the index and all that kind of stuff, because that's going to just waste your time and defeat the purpose of an open book test, Um, and of course, do not expect to find anything word for word from your book that you will use to answer a question, because that's not going to happen. I didn't get the questions from the textbook, but what's the material that's in there will help you find the answers. So kind of familiarize yourself with your textbook, especially if you haven't used it, and we haven't had a great need to use it yet. So you might want to just look through that chapter and kind of know where everything is before you start your test. Let's see. Know about your KSP. You'll have several KSP problems on there where you're like, all right, here's a solubility product. So know how to take that solid and split it up into its ions when it's dissolved in water, and know that the solubility equilibrium constant is based on the concentration of those two ions. So make sure you're familiar with that. And don't forget about the little things like the subscripts. Those little subscripts there tell you how many of those ions you're going to have. So that's going to be important too. If you have a subscript of 2, so if I have something like Hg2Cl2, well, if that dissolves in water, then I'm going to have 2 hydrogen mercury ions and 2 chlorine ions. So my concentration for each of those is going to be 2 x squared and 2x squared, x being the concentration. I don't know what it is, but they're twice as many because you have 2 of them. So just kind of be aware of that. You got to pay attention to those subscripts. Remember that if you have a equilibrium constant that is less than 1 times 10 to the negative 5. Okay, so let's kind of set up a rice table. Let's see, let's go back to our notes. And we're getting close to class time being over. And if you have to go and you don't have any questions, you're free to go. But if you want to stay on, I'm not going to rush you off either if you have questions. That's not the one I wanted to look at. Okay, I'm just going to use this as an example. So if you have this type of situation, not the square, but if you have this type of situation, and your KSP value is less than 1 times 10 to the negative 5, if it's really, really small, then we can just drop that x off. Because if you get in a situation where you're going to wind up having to use the quadratic formula or something like that, that is a signal that nope, this is not right. I can drop out that minus x, because you're not going to use that. Don't have to do that. And there would be some situations where you're going to have that. So let me give you an example. So if I have SO2, Cl2, SO2, and Cl2. And if I have 0.9 atmospheres to start with, so that's my initial conditions, 0 and 0. I make some change. So my equilibrium is, my reactants are going down, my products are going up. And at equilibrium, it's 0.9 minus x, and this is x and x. Well, if I put that into my equilibrium constant, that's going to be x squared, because x times x is x squared, over 0.9 minus x. And then I'm going to wind up having to do some crazy quadratic formula math to figure out what x is. No, don't do that. You can look at the equilibrium constant, and if the equilibrium constant is less than 1 times 10 to the negative 5, then I can just drop off this minus x thing and not have to worry about it. So let's say this is 1 times 10 to the negative 5 equals x squared over 0.9. And then I can very easily solve for x, take the square root of both sides, and get x. Okay, so just remember, if you come out with some weird thing where you're going to wind up having to use quadratic formula, then go back and look at your equilibrium constant. And if it's a really small number, you can just drop that change off. It's not going to matter. And then you'll make your math much easier. Okay. So any other questions? Anything else? I'm trying. I think I've covered everything. So don't forget the little mnemonic thing that they talked about. I think I mentioned this before, where if Q, the Q greater than K, determining which way that reaction goes, if you flip that around and put K on the left, then the less than or greater than sign will always tell you which direction the reaction will proceed in. So in this case, if K is less than Q, then the reaction is going to go to the left. If K is greater than Q, then the reaction is going to go to the right. So when you're given reaction quotient and equilibrium constant, you have to compare them. I would set it up that way. It's going to make it a lot easier for you to determine which way the reaction's going. Anything else? Don't forget about Dalton's law of partial pressure. And again, that's on your reference sheet, but just to remind you, Dalton's law of partial pressure says that the total pressure of a system is equal to the individual pressures of everything that's in that system. So your first gas plus your second gas plus your third gas plus however, whatever else is in there. So if they give you the total pressure, then you can use that to help find the pressure of the individual gases involved. So another thing to remember for your free response question. Anything else? Make sure that you've been through all of the ed puzzles. Those will be a big help to you. Make sure you've been through all the topic questions. And like I said, I'm pretty sure I have progress checks assigned in A plus in AP classroom. Not that you have to do them for a grade. It's just they're there to do extra study with, which I would strongly, yeah, there they are. I would strongly encourage you to do the progress checks because they're going to grade it for you, at least the multiple choice. They're going to grade it for you and you'll be able to see that feedback. If you do the free response ones, I'll get them graded as soon as I can. And you can see the feedback on those. So it would be a good practice test to do. And I think I have all the topic questions graded. Everybody that's done topic questions, I have graded topic questions. So. Okay. So, anything else from you guys? Okay. Are you good? Everybody good? Well, it looks like you're the last one left. Do you have any questions?